So what is the definition of the dispersion? When light rays are transmitted along the fiber, which involves some form of digital modulation, and the dispersion mechanism within the fiber cause broadening of the transmitted light pulse, and they travel along the channel. This effect is known as the dispersion. Okay. So this is so what you can see actually when it will travel through the optical fiber, so that pulse broadening it happened, and this phenomena is called the dispersion, right? And it depends on the channel length, not channel length. It is a fiber optics distance, actually how long your fiber distance L1, and you can see here fiber output at distance L2 greater than L1. So this is if your cable length is more actually, so what will happen, dispersion it will be more. So you can see that you can't distinguish actually which one is zero. Now it is totally changed, your data has totally changed, and this overlapping part is called the intersymbol interference. Okay. And it happened that what you called where it will happen in the receiver part. You can see that each pulse broadening and the overlap with the neighbors even become the indistinguishable at the receiver in output, and so this effect is known as the ISI. Okay, so that is very important, this one, that ISI. So you have to, for no overlapping, actually, you have to maintain some bit rate. So that digital bit rate BT must be less than the reciprocal of the broadened pulse duration. So that you have to maintain this one actually whenever you are sending the data. Okay, so this is very important actually. The digital bit rate BT must be less than the reciprocal of the broadened pulse duration. Lambda is your pulse broadening due to the dispersion on the channel. And this is the maximum bit rate for the optical channel actually, that this is a maximum bit rate you want to follow. You can mute your mic actually. So here one thing is there actually. What is that NRZ? NRZ means it is a non-return to zero. Okay, so what is that meaning actually? Whenever you have a pulse, suppose if this is the pulse actually, so if this is my time period, so your that whatever amplitude, it will not come to the zero. So that is the meaning of NRZ. Okay, non-return to zero. If you consider one pulse, if I consider only this pulse, okay, this is my period actually. So in this particular period, you can see that your amplitude is constant. Okay, it is not coming down to zero. Now RZ means what it is? RZ is a return to zero. So if I consider it is a one pulse, so in that particular pulse, you can see that there is a zero here. That is the reason actually, that is a return to zero. And you can see that these are the relation actually. What is that for RZ, B optical and BT max? So few relation you have to follow for non return to zero and return to zero. So this is very important actually. See here actually, this is what basically it is. It is a multi-mode step index optical fiber, right? This is multi-mode. So you can see that these are the multi-mode step index optical fiber. This is multi-mode graded index optical fiber, and this is a uh, single mode step index optical fiber, right? So already we have discussed actually for multi-mode means what? There are different mode will be there, and step index is nothing but your core. Actually you have a constant refractive index, and your cladding also you have a constant refractive index, and your core refractive index is more than cladding, right? So you can see that this is my n1, and this is n1, and this is n2, and this is the profile actually for multi-mode step index fiber, and this is the things actually. So if we have a input pulse, so what we can see here, okay, so this one actually, that broadening is output pulse, means at our output dispersion effect is more, right? Now if you have a multimode graded index, so what you can see here for multimode graded index, if you remember that what it is, so your core refractive index is changing actually in your what is that axis, core axis, your refractive index is more, then slowly it will start reducing, and at this cladding again it is a n2 constant, okay, this cladding it is a constant. So that is the reason actually we'll be getting this kind of profile. You can see that it is not a constant, it is like, you can see that if I take this one, right? So it is changing, and where it is maximum, your maximum at this point. At this point is the maximum, and this is nothing but it is a core axis. All of you are able to follow? And you can see that your refractive index, it is start reducing, and you can see that this is my cladding refractive index. And for graded index, actually, what will happen for graded index? This is my input pulse, and you can see that compared to the step index, graded index, you can see that sharpness is little good. So why it is happening actually? So you can see that whenever you are considering the multi-mode, so what will happen? There are different refractive index, right? There are in this core actually different refractive index is there. So you can see that at this point, okay, and you can see that these are all at different refractive index, and whenever light is passing from high refractive index to low refractive index, right? And whenever light is passing from high to low, so what will happen? Your light refracted ray, it should be away from the normal. Okay, so like that your light is traveling, and when it comes to here, the total reflection it is happening, and it is coming down. In that case, you can see here it is light is traveling from low refractive index to high refractive index, right? Okay, and you can see that your bending, it will be near to your normal. Okay, and for here actually there is nothing like that. Light straight way it is following that path, it is following the straight, but in this graded index, it is like a bending, it will happen. Okay, now if you see here at this point, if I consider, if you see this ray, if you consider this ray, and if you consider whatever light is traveling along with the, okay, So light is moving from here to here also, here to here also. So if I consider the red and pink line, okay, that whatever light is transmitting, you can see that it required the, what is that, less path it is traveling, right? But it is that rate, it will be the slower. Here actually it is traveling the more path. Okay, you can see that traveling path will be more, but it is a very faster rate. Are you able to understand? So that is the reason for graded index actually, that this two almost it will reach at the same time. That is the reason actually your dispersion is less compared to your step index, multimode step index optical fiber. Okay, so this is the reason actually, you can see compared to this, this is better. Multimode is always better, right? Now for single mode step index, if you remember, for single mode step index, only one mode is present. Okay, so one mode is present, and you can see that your diameter will be very, very small. Okay, you can see that diameter is small and cladding will be more. Okay, and there is only one mode is present. So intermodal dispersion, now we'll come to that actually, what is the intermodal. So here only one mode is there, and you can see that intensity, it is good actually compared to all three. So that is the advantage for your single mode step index optical fiber. Your dispersion will be less compared to all. But here it will be very costly. Okay, that diameter less and only one single mode, that fabrication process will be little bit difficult here. Okay. So this is a three type of fiber illustrate the pulse broadening due to the intermodal dispersion in each type. So you can see that some comparison they have given actually. Multimode step index exhibit the greatest dispersion or mode pulse broadening. This is multimode graded index, considerably improved performance, because you can see that it will be dispersion is little less compared to that previous one. Single mode, you can see that minimum pulse broadening and thus capable of greater transmission bandwidth in gigahertz range. Okay, so it is always, it is very much good actually for single mode step index. And already I have told you actually, this is very, very important. That is amount of amount of pulse broadening, it depends on distance of the pulse travel within the fiber. This is very, very important actually. Already in first diagram only we have showed to you. So this is very important. Then measurement of the pulse broadening is represented over the length of fiber nanosecond per kilometer. Okay, so this is the measurement, and this is very important actually. You have to solve few problem also using that. That is the information carrying capacity of the fiber is usually represented as bandwidth length product. This is very important. Okay, how much information it can carry. Your fiber optics, it can carry how much information. It represent bandwidth into length. Length, that is very important. B optical into L. Okay, so you have to remember that. That is what is that. If you have a notes actually, you can mark also that which part is important. Okay, so this is actually very, very important. That is the information carrying capacity of the fiber, and this is the B optical bandwidth into L. Okay, bandwidth into L product for three fibers. As you can see that this is already it is written actually. This is for MMSI is 20 megahertz, 1 gigahertz, and you can see that 100 gigahertz per kilometer. Okay. Now, in order to appreciate reason for different amount of pulse broadening with the various type of optical fiber dispersion mechanism is to, okay. So now we have to learn, actually there are different type of dispersion is there. Okay, so we should learn that one. One is called the chromatic dispersion. What is the meaning? And it is one more name is called the intramodal dispersion. What is that intermodal dispersion actually? Uh, and it will be there for all optical fiber. Okay, why basically it is happening? So when we'll be using some laser source, right? And that whenever a laser source will be using for and that particular optical source, actually it will not transmit only one frequency. Okay, it will be like this. Your spectral, actually that input, it will be like this. Okay, and if I draw, actually and this is nothing but, this is your lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. So this is the maximum wavelength and this is the minimum wavelength, and this is the your whatever optical source will be there, this is the spectral. Okay, spectral for that. And it is not that it will transmit only one single frequency. Okay, it will be transmitting on the band of frequency. So that is the reason, actually you can see here, it may occur for all type of optical fiber. That intramodal dispersion, it is there for all the optical fiber. The final spectral lining of the optical source, you can see that it is a, because that you have a optical source, this is a finite, some line width will be there, and optical source do not emit just a single frequency. That's what I told you. This is very, very important. This is optical source do not emit just a single frequency, but a band of frequency. That's what I told you. So this is my optical laser source, actually. This is the spectral of your input. And you can see that it is not only one single frequency. Okay, there are minimum frequency and maximum frequency. So different frequency, because of the obviously it will reach to different time, right? So propagation delay and all those things, it will come into the picture. So that's why you can see that the propagation delay difference between the different spectral component transmitter signal, and this causes broadening of the each transmitted mode and hence the intramodal dispersion. Okay. And this is very, very important, actually, the intermodal dispersion. Basically, why it is happening for intermodal dispersion? Your optical fiber, optical source, whatever LED you'll be using, infrared LED, whatever it is, okay, it has a finite spectral line width, okay, and it will not emit one single frequency. It will emit broad band of frequencies, okay. And obviously your lambda 1, lambda 2, lambda 3, if your minimum frequency is lambda 1 and maximum frequency is lambda 6 or lambda 8, okay, so definitely you will be having some difference of delay, propagation delay, right, because it is transmitting in the different wavelength. Okay, and that is the reason, actually, that some broadening it will happen. So that is called your that intramodal dispersion. Okay, there are and it depends on the waveguide material also. Okay, and it also guidance effect within the structure, that is a waveguide dispersion. There are two type of, again, dispersion is there. One is material dispersion and one is waveguide dispersion. Okay, so whatever are you able to listen anything? Hello, hello, hello,
Yeah, ma'am, we can listen, ma'am.
are you able
Hello?
to follow anything?
Yeah, ma'am.
Just check who all is there. Akash, are you present? Akash?
Yes, ma'am.
Yeah. So you are able to understand anything?
Yes. Yes, ma'am.
Can you please tell me what is that chromatic dispersion? No, I explained, right? Chromatic dispersion, intermodal dispersion. You have a optical source, and that particular optical source has different frequency, and it will travel in different time actually. So that is the reason we will be having broadening of the pulse. This is the material dispersion. Okay, so what is the meaning of material dispersion? So pulse broadening due to the material dispersion result from different group velocity of the various spectral component launched in the fiber. So whatever I told, they have written actually. So you should understand that what is the meaning of phase velocity and group velocity. Okay, so what is the meaning of phase velocity? Phase velocity is the individually, suppose you have 5 wavelength signal, okay, lambda 1, lambda 2, lambda 3. Okay, so all 5 individual that no, it is traveling whatever velocity, it is called the phase velocity. Okay, suppose lambda 1 is, suppose you have a 5 wavelength some signals are there, lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, lambda 5. Okay, so each wavelength, it is flowing at its particular velocity, it's called the phase velocity. And whenever, and group velocity is nothing but all together, okay, that resultant waveform will get, right? So that whatever resultant waveform will get, that particular waveform, okay, what velocity it moves, it's called the group velocity. Is it clear to you? So if I just want to draw this one, this is very important concept actually. Suppose if you have this kind of waveform, okay, and one more waveform, if you have this, okay, and if I do this, if I do this plus this, okay, so I'll be getting some resultant waveform. Suppose if I'm getting like this, okay, so please understand what is the meaning of, because this is very important. Every time they'll be asking what is the group velocity and what is the phase velocity. So suppose this is my lambda 1 wavelength and this is my lambda 2, and there are two different wavelengths, and each wavelength, whatever velocity it is flowing, actually this is called the phase velocity. Okay, but whatever I'll be getting after, if I add this two wavelength, okay, and we'll be getting this kind of frequency, some wave we will get. This is the resultant of this two, right? And what velocity it will move, actually this is called the group velocity. Okay, if I do the grouping, then whatever result I will get, that particular waveform, whatever it will travel, so in that way we'll get the group velocity. Okay, that is the reason you can see that pulse broadening due to the material dispersion result from the different group velocities of the various spectral component launched in the fiber from the optical source. That's what I told you, right? Same thing you are able to follow? different group velocity at that, no, it is following in the different group velocity, so we'll be getting some dispersion. The material is said to exhibit the material dispersion when the second differential of the refractive index with respect to lambda is not 0. Okay, so this is a condition. Actually, the material is said to exhibit the material dispersion when this is the second derivation of Ri with respect to lambda is not 0. That means d2n by d lambda square not equals to 0, right? And this is the pulse spread due to the material dispersion may be obtained by considering group delay this g in the fiber, which reciprocal of the group velocity vg. This is some formula they have written actually, so you need to understand that how we have got it. So lambda g equals to 1 by c n1 minus lambda dn1 by d lambda, and this is the pulse delay tau m due to the material dispersion in the fiber of the length L is. So this is the how much delay we are getting due to the dispersion. This is the formula for that. Okay, and this is very important. You will be using some kind of this uh, for source with RMS spectral width lambda sigma lambda and mean wavelength lambda, RMS pulse broadening due to the material dispersion. It is a that pulse broadening due to the material dispersion, and this is a relation of that. Okay. So now whatever you have, actually you have to do the differentiation. Whatever d this tau m by d lambda, we have to do the differentiation. You have this tau m, right? So you need to differentiate this equation number. I don't know, they have not given any equation here, so we can just write down the equation if you want to write. So this equation, so this equation you need to this is the equation number 1 if I write. So you need to do the d tau m divided by d lambda. So you have to do the differentiation for this equation number 1, and you have to substitute at this point, and finally we'll be having some kind of result. So this is very important actually. That this is like a formula only, this is a dispersion of the material equals to m dot tau lambda into L. Okay, and this is m is nothing but this one. This part is called m. Okay, so sometimes you have to use this. Not L is the length. Material dispersion parameter m defined as, and you can see that expressed in per second, per nanometer, per kilometer. All of you please go through this particular problem. Nothing is there to explain here. You can just need to see actually how we can solve this particular problem. Whatever we have used that formula before, it was there, so you have to use those formula and have to solve the problem. Bandwidth L product for the fiber. So you should know the bandwidth into L. L is how much? It is 15 kilometer. So substitute that bandwidth, you have to find out. So that also they have given, this is the multimode gradient index exhibit total pulse broadening of 0.1 microsecond over the distance of 15 kilometer. Okay,